All right, so we are going to talk about the review for the bonding unit. Now, first off, how many valence electrons do each of the main group families have? So that is just whatever column it's in, that's how many valence electrons it has. So column, I have the wrong thing here. So column 1 has 1 valence electron, column 2 has 2 valence electron, 3 is 3, 4 is 4, 5 is 5, 6 is 6, 7 is 7, and 8 is 8. So the main 8 columns of the periodic table, that's how many valence electrons they have. Next, what is the octet rule? How does it apply to bonding? So the octet rule just says that elements want to have 8 valence electrons in order to be happy and stable. That's the whole purpose of bonding. Almost all the elements on the periodic table do not have 8 valence electrons, and they want 8 valence electrons. So in order to get those 8 valence electrons, they bond with other elements to either transfer or share those electrons so they can have 8 electrons around themselves and fulfill the octet rule. The 3 bond types are ionic, polar, and nonpolar. For an ionic bond, electrons are transferred from one element to another. Okay, so for example, if we have sodium and chlorine, sodium has 1 valence electron, chlorine has 7 valence electrons, like that. The chlorine is going to steal that 1 valence electron and bring it over here. And the new situation is going to be Na, that has 1 less electron and is going to have a positive charge, and Cl, that now has 8 valence electrons and has a negative charge. Oh, that's not a very good negative. Sorry, I'm going to do that again. A negative. There we go. A negative charge. So that's an ionic compound. A nonpolar bond is when you have electrons being shared evenly between the 2 elements in the bond. So for example, if we have nitrogen bonded to nitrogen, okay, the electrons in that bond are right in the middle of both of them. They both, since they're the same atom, have equal electronegativities, so they are pulling on the electrons equally, so the electrons are right in the middle being shared equally. Now, if we have a bond between 2 different atoms, so for example, we'll say nitrogen and chlorine. I changed my mind, nitrogen and fluorine, I like that better. So we have a bond between nitrogen and fluorine, okay? Fluorine has a higher electronegativity, so the electrons are still going to be being shared, but the electrons are being pulled more towards the fluorine than the nitrogen, because it has a higher electronegativity. So that is a nonpolar bond. So again, this is ionic, this is nonpolar, and this is polar. What relationship exists between electronegativity values and bond type? Okay, so when we have a large difference in electronegativity values, that is more of an ionic bond or a polar bond. If we have a small difference in electronegativities, that is going to be a nonpolar bond. Okay, so valence electrons determine the type of bond. So an ionic bond, we kind of already said that, but an ionic bond is when you have electrons that get transferred between elements as opposed to being shared between elements. What do electrons do to form an ionic bond? Electrons get transferred. Electrons go from one atom, they leave that one atom, and they get picked up by a separate atom. What defines a covalent bond? Be sure to include types of atoms and electronegativity differences in your answers. So a covalent bond is when you have 2 atoms that are sharing electrons, and when you have a smaller difference in electronegativities. All right, how are Lewis structures drawn? What rules dictate the use of dots and lines? So, Lewis structures are drawn by first, so there's steps. First, we are going to find how many valence electrons we're going to find how many valence electrons each element in the compound has. Once we find how many valence electrons there are, we are going to then find the skeletal structure of the compound. Skeletal structure basically meaning what is the central atoms, okay? After you put the central atom in the middle and the peripheral atoms on the outside, then we take all our valence electrons and we fill them in around the outside atoms. If we run out of atoms, if we run out of electrons, then we are going to check and see if all of our atoms are happy or not. Now, what I mean by happy is, do they all have 8 electrons around them? If all atoms are happy, then we're good. If all atoms are not happy, then we're going to have to start doing double or possibly triple bonds. Okay? How can you tell from a Lewis structure if a given compound is an ion? If it is an ion, it has brackets and the charge around it. How does bond length and strength relate to the type of covalent bond? The single bonds are the longest and weakest. Triple bonds are the shortest and strongest. And double bonds are in the middle. Resonance. Resonance is when you have another possible structure that would be a correct structure. So if you have double bonds and those double bonds could go in 2 different places or 3 different places or 4 different places, that is resonance. Okay, so now we have some Lewis structures. All right, so CO2. First things first, we got to find the valence electrons of each thing. So carbon has 4 valence electrons. Oxygen has 6 valence electrons, and there are 2 of them, so that's a total of 12 from the oxygen. We add them together, we get a total of 16 valence electrons. Next, we do our skeletal structure. Carbon goes in the middle, oxygen goes on the outside. We do our bonds. I'm going to zoom in a little bit because I like that better. So we do our bonds. We have so far used 4 valence electrons. So we subtract 4 from our total. So we have 12 left. We are going to distribute those 12 valence electrons. So, why did that not work? There we go. 2, 4, 6, 8, 10, 12. Notice we distributed them to the outside. Okay. Now, we used all of our valence electrons. We have 0 left. So now we're going to check and make sure everything's happy. Oxygen's happy. It has 8 valence electrons around it. This oxygen's happy. It has 8 valence electrons around it. Carbon is not happy. It has 4 valence electrons around it. So we are going to take this set of electrons and we are going to move it into a double bond. So just like that, and then we have to erase these 2. Now, carbon has 6 valence electrons around it. It's still not happy. It's more happy, but it's still not happy. So we got to take another set of valence electrons and move them to another double bond, just like that. And then we have to erase them from up here. Whoops, that's not erasing. There we go. And there we go. That is our final Lewis structure. All right, next, SO4 minus 2. So S has 6 valence electrons. O also has 6 valence electrons, but there are 4 of them. So that is 24 from oxygen, 4 plus 6. That gives us a total of 30. And then we have a negative 2, which we have to add to it. So that's actually 32 valence electrons. All right, the S goes in the middle because it is listed first and because it is there's only one S. We put our oxygens around there. Also, I should have said this earlier, but carbon goes in the middle for the previous one over here because number 1, carbon always goes in the middle. Number 2, there's one of them. And number 3, it is listed first. Okay, so we have S and 4 O's. We have so far used 8 valence electrons because there are 4 bonds. So we have 24 valence electrons left. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, so we used all 24 of our valence electrons, and all of our elements are happy. So this one's done, except since this is a ion, we put brackets around it, and we do -2. Next one, NO3, negative. So N has 5, O has 6 times 3, so that's 18. And then we have our -1 here, so that's 1. So 5 plus 1 is 6. 6 plus 18 is 24. So we have 24 total valence electrons. N goes in the middle. O's go on the outside. We used 6 valence electrons so far. So we have 18 left. So 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, we used all 18. All of our O's are happy. Our N is not happy. So we're going to take one of our pairs of electrons, put them in here, and do a double bond, and then get rid of the ones in here. Now, I could have done that with this one over here and used a double bond here, or I could have done that with this one here and used a double bond here. That is what resonance is. Resonance is being able to put a double bond on any one of these and still being correct. So that's that. We also still need our brackets because this is a ion. And now we're done. All right, next one, HCN. H has 1, carbon has 4, nitrogen has 5. So that's a total of 10. C goes in the middle because C always goes in the middle. H on one side and on the other. Bonds. We have so far used 4 valence electrons. We have 6 left. So 2, 4, 6. Hydrogen's happy because hydrogen only needs 2. It is an exception. Nitrogen's happy. Carbon is not happy. It only has 4. So we are going to take this lone pair and this lone pair and put them there and do a triple bond and erase them from here. And now we're good. Carbon's now happy. It has 2, 4, 6, 8 valence electrons around it. All right, NH3. We have N is 5, H is 1 times 3, so 3. So that's 8. N goes in the middle. H goes on the outsides. We have so far used 6 valence electrons. We have 2 left. H's are already happy, so we're not going to put any there, but N is not. There's our last 2, and we're good. NH4. N, still 5. H is 1 times 4. So that is going to be 9, but since this time we have a positive charge, we are going to subtract 1. So we have a total of 8. N goes in the middle. H's go on the outside. Oh, I should probably say that. So we used 2, 4, 6, 8. That's all of them. H's are happy. N is happy. We're done, except for our brackets. We put brackets around it and do +1. All right, H2O. H has 1 times 2. O has 6. We have a total of 8 valence electrons. O goes in the middle, because H's can't ever go in the middle because they only can have 2 valence electrons. We have so far used 4 valence electrons. We have 4 left, 2, 4, and that's it. We're good. Come on, there we go. All right. Next one. We have C is 4, H is 1 times 2 is 2, O is 6. So that is 12 total valence electrons. Carbon goes in the middle because it always does. H's go on each side, and O goes on top. Doesn't really matter what order that is, but that's just the way I like it. Put our bonds. We've so far used 6 valence electrons. We have 6 left. So we fill in oxygen, 2, 4, 6. We've used all our valence electrons. Carbon is still not happy. So we erase one of these on oxygen, put a double bond, and we're done. All right, what does VSEPR stand for? So VSEPR is valence shell electron pair repulsion. And basically all it means is that electrons, which are negative, repel each other. And so when they are participating in bonds in a compound, those bonds want to be as far apart from each other as possible. So that's what the repulsion part of VSEPR is. They repel each other, and so therefore they make shapes based on where, based on how they repel each other. All right, so your bonding domains. When you have a linear shape, that means you have 2 bonding domains, 0 non-bonding domains. I'm not going to sketch it out, but that's the sketch is going to be the 3-dimensional model of that. So linear has 2 atoms bonded to the central atom, 0 lone pairs. Bent is going to be similar to that. It's going to have 2 atoms bonded to the central atom and 1 or 2 lone pairs. Trigonal planar is going to have 3 atoms bonded to the central atom and 0 lone pairs. Trigonal pyramidal is going to have 3 atoms bonded to the central atom and 1 lone pair. Tetrahedral is going to have 4 atoms bonded to the central atom and 0 lone pairs. All right, so to predict the shape of a molecule, first thing you got to do is do the Lewis structure. I'm not going to narrate the whole Lewis structures again because I already did in the previous one. And actually, these are all the same ones anyway. So you should have those already taken care of. So CO2 has 2 bonding domains and 0 non-bonding domains. So that's going to be linear. I'm just going to do the first letter. SO4 has 4 bonding domains and 0 non-bonding domains. So that's going to be tetrahedral. NO3 has 3 bonding domains and 0 non-bonding domains. So that's going to be trigonal planar. So trig plane. Trigonal pyramidal also has those same initials, so that's why I wrote it out that time. HCN has 2 bonding domains and 0 non-bonding domains, so that's going to be linear. NH3 has 3 bonding domains and 1 non-bonding domain, so that's going to be trigonal pyramidal. NH4 has 4 bonding domains and 0 non-bonding domains, so that's going to be tetrahedral. H2O has 2 bonding domains and 2 non-bonding domains, so that's going to be bent. CH2O has 3 bonding domains and 0 non-bonding domains, so that's going to be trigonal planar. Okay, what is a dipole? So a dipole exists when you have a polar molecule. Now, a polar molecule has two poles. Makes sense, right? Dipole. Now, the poles are produced when you have the polar molecule and it has um, two different areas of electron density. So when you have, let's say, pH 3, and we have our lone pair here. Okay, so the P is more electronegative than the H's. So the P is pulling the electrons up this way, and the H's are not pulling as strongly. So the electrons are kind of hanging out more towards the P's than the H's. Okay, so the density of electrons around the P is greater. And since electrons are negative, we have a partially negative charge around the P and a partially positive charge around the H's. Now, it's only a partial negative and partial positive charge because the electronegativity difference between P and H is not strong enough to just totally pull the electron away from the H's, just enough to kind of like start winning a tug of war kind of thing. The electrons are just kind of hanging around the P a little bit more than the H's. It doesn't pull them all the way off, but just pulls them towards it. So that's the situation with the polar molecule. So this is our dipole. We have a negative pole up here on top towards the P and a positive pole down here towards the H's. So number 16 that we kind of just talked about, that partially positive and partially negative. It's because the electronegativity is not strong enough to totally pull the electrons off of the other atom, just partially. All right, how do you determine if a molecule is going to be polar or nonpolar? Now, first off, if it has only nonpolar bonds, it's nonpolar. Makes sense, right? So, for example, a bond between N and N, that's a nonpolar bond because they're the same atom. Also, a bond between C and H, that is a nonpolar bond, just because C has a very similar electronegativity to H. Now, if we have a bond between C and Cl, that's a really big L. I don't know why I made it that big. Cl, there we go. Then that is a polar bond because they're two different atoms. Okay. Now, if we have polar bonds, a lot of the time that means we have polar molecules, but not always. This is kind of a little tricky situation. So, for example, if we have carbon dioxide, okay. Now, this bond here, that's a polar bond between O and C. This bond here, that's a polar bond between O and C. Okay, so this has polar bonds. Now, since these are polar bonds, the oxygen is more electronegative than C. So the oxygen is pulling the electrons towards them away from the C. Okay, so the electrons are trying to hang out more towards the oxygen. But since this oxygen is pulling that way and this oxygen is pulling that way, they're pulling in opposite directions, and they're pulling with equal strength because they're both oxygen, so they pull with equal strength. Those pulls are going to cancel each other out. So think of it like a tug of war. We have a rope traversing its way through the whole molecule. Okay, the oxygen is pulling on this side, the other oxygen is pulling on this side. They are both pulling with equal strength and in exact opposite directions. If that happens, the rope doesn't move, right? So that means they cancel each other out, and this is a non-polar molecule, despite it having polar bonds. Now, another similar situation, let's say we have water, H2O. So H2O is similar, but a little bit different. H2O still has two molecules on the outside, but instead of being oriented in a linear molecular geometry, it's oriented in a bent molecular geometry. So that being said, in this case, oxygen is the more electronegative one. So the oxygen is pulling this way and this way. But since it is bent,
they are not going to cancel each other out because they are not it's not pulling in equal and opposite directions. Okay, it's pulling at an angle like this. So the reason why it's pulling at that angle is because of these lone pairs. These lone pairs make it so that they're bent instead of straight. So when we have a molecule that does not have lone pairs like this on the central atom and is symmetrical, those bonds are going to cancel each other out, and it's going to be a nonpolar molecule. This is also assuming that the atoms on the outside are the same atom. I'll talk more about that later. If we have a molecule that does have lone pairs on the center, that kind of offsets the symmetry a little bit, and that makes it so that the bonds are not pulling in they're not pulling in opposite directions, so they don't cancel each other out, and therefore the bond is polar. Okay, so this situation over here works with tetrahedral and trigonal planar molecules. If you have tetrahedral, trigonal planar, or linear, and all of the atoms are the same on the outside, then that is going to be a nonpolar molecule because all of the bonds are going to cancel each other's poles out. If you have bent or trigonal pyramidal with lone pairs on the outside of the central atom, then that is going to that is going to not cancel the poles out, and it will make it so that it is a polar molecule. All right, so let's say we have tetrahedral. So we have C, Cl, 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 Cl. Okay, now in this situation, these bonds are going to cancel each other out, right? And that will be a nonpolar molecule. Now, let's say we have this instead. In that case, all the bonds are pulling oppositely, but not equally. These are pulling equally, but this is not pulling equally. So that is going to be a polar molecule because this bond is not going to cancel out all the other bonds. Okay? All right. Next, we're determining the polarities of the compounds here. So we already wrote down in the previous question the Lewis structures and the molecular geometry. So we're just going to talk about the polarity and why they are polar. So first one, CO2 is nonpolar. We already talked about that because that is linear. Bonds cancel each other out. SO4 negative 2, that is tetrahedral, and the bonds or the atoms are all the same on the outside, so that is nonpolar. NO3 minus, that is trigonal planar, and all the atoms are the same on the outside, so that is again non-polar. Excuse me. Those are all of three of these. They do not have lone pairs on the central atom, and all the bonds on the outside are the same, so they're all nonpolar. Now, HCN, we're going to draw this one, just a basic version of this one real quick. So this is linear, so it would cancel each other out, but the two atoms on the outside are not the same. So they are not going to pull with equal strengths. So this is polar. All right, NH3, that is a trigonal pyramidal. So trigonal pyramidal is, if it has polar bonds, is going to be polar because it does have lone pairs on the central atom, and it will not cancel the bonds poles will not cancel each other out. NH4, on the other hand, is tetrahedral, so that is nonpolar. H2O, we already talked about that one. That is polar because it is bent. And CH2O, that is going to be trigonal planar, but it's going to have two different types of bonds. Whoops, that's a bad H. Sorry, there we go. So this oxygen is going to pull with more strength than either of these hydrogens, so that is going to be a polar bond. Okay, so for intermolecular forces, we're going to talk about all the details of those. So first off, we have three different types. We have London dispersion, we have dipole-dipole, and we have hydrogen bonding. London dispersion is the weakest. Dipole-dipole is in between. And hydrogen bonding is the strongest. Okay, now when do we have each of these things? Well, London dispersion exists in all molecules. So every single thing, every single molecule that exists has London dispersion in between the molecules. So if we have a nonpolar molecule, that has London dispersion. If we have a polar molecule, that also has London dispersion. Okay. Now, dipole-dipole only exists in polar molecules. Polar molecules. Okay. Now, if we have dipole-dipole, we also have London dispersion. Okay. So just because we have dipole-dipole doesn't mean the London dispersion goes away. It just exists alongside the dipole-dipole. Hydrogen bonding exists in polar molecules that also have hydrogen bonding to nitrogen, oxygen, or fluorine. Not all of them, just one of them. So if hydrogen is bonded to one of these three atoms within the molecule, and it's a polar molecule, then the molecules have hydrogen bonding intermolecular forces. All right, so relative freezing and boiling point. London dispersion has a pretty low relative freezing point as well as boiling point. So I'm just going to do low like that. Dipole-dipole has a higher relative freezing and boiling point. So higher. And then hydrogen bonding has the highest freezing and boiling points. And the reason being is because as our intermolecular forces increase, as the strength of them increases, they pull the molecules together with more strength. And as we know, freezing and boiling, as we melt and boil, the molecules get further apart. And so if we have stronger intermolecular forces, it takes more energy to pull them apart. So therefore, their freezing points and boiling points are higher as the intermolecular forces get stronger. All right, so what bonds must be present for a compound to be able to exist in hydrogen bonding? We already talked about that. Hydrogen bonded to N, O, or F. What type of intermolecular forces exist between oxygen molecules? So if we have oxygen bonded to another oxygen, that is a non-polar molecule. If it's non-polar, it does not have dipole-dipole. It does not have hydrogen bonding, but everything has London dispersion forces. So that is the only thing that it has. What type of intermolecular force exists between water molecules? So water molecules, as we have said earlier in this video, are polar. Okay, so since they're polar, they have London dispersion because everything does, dipole-dipole because it's polar, but also this hydrogen is bonded to this oxygen, and that is one of the options for hydrogen bonding as well. So this has London dispersion forces, dipole-dipole, and H bonding. All right, what type of intermolecular forces exist between methane? So methane, which is CH4 with all the H's on the outside. This is a polar molecule because number one, C and H, that's a non-polar bond. But also, even if it was a polar bond, this is tetrahedral with no lone pairs. That's the word I'm looking for, with no lone pairs on the central atom. So even if it was a polar molecule or polar bonds, the polar bonds would all cancel each other out. So this is a non-polar molecule, which means only London dispersion forces. Least to greatest strength, we already talked about that, but just in case, London dispersion forces is the weakest. Dipole is the second weakest. I don't know why I wrote that second dash. Hydrogen bonding is the strongest. And I believe that is it. Yep. All right.